Hello everybody, Mr. Hinnon here with another Henstitute video. This one is on the history of electricity. We've watched the electric vocabulary, so we have some of those terms. I thought I would kind of go through those people and then kind of extend on how things kind of fit. So we started off with good old Thales of Miletus up here, and when we talk about Thales, one of the key things that we like to talk about is he rubbed amber against animal fur is kind of the first observations of static electricity. So that was kind of the beginning. That's why we liked Thales. And then William Gilbert really didn't do anything except realize that he could use the Greek word for electron from amber. So he starts using the word electricity, that type of stuff. Then, if you keep going from there, probably Charles Dufay is our most popular because he started to actually kind of lump them into different categories we saw. So he starts noticing if you take a variety of things and rub it against materials, that you could charge them up or electrify them. And you can get all kinds of things happening, and starts putting them into different categories and how they kind of fit. I thought this one was just funny. It shows a picture of a small boy who is actually being suspended from silk cords. And what they would do is they would actually charge him up. So he's got some kind of charged rod here that's going to be, and then he'd touch him, and then other people would just come along and touch the little kid and get shocked. So it's just kind of a funny situation that they would do stuff like that. But here is our father of electricity, good old Ben. 1700s. That's the best way to kind of think of him. He's the one that coined all the main terms. He's going to come up with the idea of electricity. So really all those different electrical phenomena that we kind of think about, that's we attribute to Franklin. And in fact, he even wrote books about it. So we've got the experiments and observations on electricity, all the things that kind of fit with that. With that in mind, he's the one that's coining all these terms: charging, discharge, battery, electricity, electrify, armatures, all the lovely stuff, and we get it. But one of the things he's also famous for that we tend to think of is we tend to think of him flying a kite in a thunderstorm. So I like this kind of picture over here because what it's trying to let you know is back here is supposed to be the kite. So I don't know if you can see it real well. I'm trying to highlight it in here. But the idea is this kite, it wasn't supposed to actually be in the thunderstorm itself. It was supposed to fly up next to the thunderstorm. So here's our kite. And the idea is we had clouds up here, these storm clouds. And if the storm clouds were around it, the storm clouds are building up something. We don't know what this is, but he thought it was some kind of electricity. They were getting electrified. He thought if he could put this kite up there, it would also get electrified. So it would be like a little storm cloud. So it would get some kind of electricity built up. Then the string, I'll just kind of run it down, would run all the way down. And they have this little Renaissance version with little cherubs helping him and everywhere. But one of the other things that we always think of is he had a key attached to this. Now, we always, whenever you talk about it, we always talk about he flew a kite in a thunderstorm and it got struck by lightning. He's not trying to get struck by lightning. What he's trying to do is actually bring the electricity up in that storm cloud down to Earth. So this string would have probably been soaked in salt water, which we now know salt water is actually a very good conductor of electricity. It allows charges to move through it. They just knew that result. They didn't really know the reasoning probably behind it. But his thought was if he could make this electrified up here, like a storm cloud, then his little storm cloud kite could travel down to here. And then I like this picture because what it's trying to show is then a little bolt of lightning would go to him and he would get a little bit of a shock. Now, we don't think he actually probably did this experiment, or it probably didn't work as well as he was hoping, because that could store, or it could actually charge quite a bit and it would definitely damage him. Probably more likely he used a Leyden jar to actually store the charge and then use that to do something else. But who knows? He might have been that crazy. The other thing that we like to bring up is he came up with this idea of the law of conservation of charge. He didn't think you were actually creating or destroying charge. He thought that charge was just a single fluid that would move between things. So everything had this charge fluid in us. And when I make something positive is when I'm adding this charge fluid. So I get a big amount of this charged fluid. And when something becomes negative, I'm losing it. So a negative only is basically a loss of that charge. So this was really working well because it switched over from the older idea of having two different kinds of fluid. They thought there was positive fluid and negative fluid. He said you don't need that. You just need one. And as it adds to it, it builds it up. And when it decreases, you're good. So I thought that was a great idea. Now we kind of have a feeling for what he's actually doing. So I put this in here to talk about triboelectricity. Triboelectricity is actually the process of transferring electric charge from one object to the other using friction. So the way it works is, let's say that I take this ebonite rod and I rub it against animal fur. Well, ebonite is really just a fancy way of saying rubber material. Okay, this is a rubber material. So when I rub these two materials together, what I can do is I can look at a triboelectric series. And in this triboelectric series, the higher you up, you have an increase in attraction for electrons. We're going to talk about that in a little bit. But basically, we know the electrons are negative. So you have an increase of an attraction for negative charge. So anything high on the list would actually have a negative charge. Anything low on the list, like this fur, would tend to be positive. So this is positive, this is negative. So when I take rubber and I rub it against fur, or if I take a balloon and rub it against my hair, that rubber will pick up a negative charge because it has more attraction for electrons or more attraction for negative, and the fur will actually be positively charged. What Franklin thought was happening is as you were taking the piece of rubber and rubbing it against your fur, you were actually taking the positive fluid off of the rubber and putting it onto my hair. So my hair would become positively charged, or animal fur would be positive because it gained this fluid. I'll try another one. So another one that we often do is we take glass and we rub it against material. So glass, the reason why we do that is it's low on this list. And if you rub glass pretty much against anything, in my case, I'm talking about rubbing it against the fur up here. Now it's kind of the reverse. Glass is actually more positive than the fur. So if this was a piece of glass that I rubbed on this animal fur, this was fur. Now what would happen is the glass would actually gain the positive charge, and the fur would actually be losing the positive charge. We now know it's actually the fur would be gaining electrons and the glass is losing them. We're going to talk about that in just a second. So it's kind of a neat one. If you know a triboelectric series, you can always kind of look at how they're related to each other. This is just another one about the conservation of charge, that you're not actually creating it. We know how charges affect each other. If you have unlike charges, we often say opposite charges, they attract. Whereas if you have like charges, they repel. So that's really all we have here. Just keep moving. Charges, when we talk about conductors or insulators, it's a matter of whether it can conduct or allows charges to move through it. So what we're thinking of is we know that when we have something hot, that heat can move from hot to cold. Same thing happens here is if we have negatively charged objects, we have negative charge moving. So this is a good conductor. Whereas we also talk about things that are good insulators. In other words, they don't allow charge to move through them. For example, the balloon I was using earlier, or talking about earlier, or the rubber ebonite rod. You can also cause what we call temporary induction in stuff. So if you were to take a balloon and rub it against your hair and then stick it to a wall, for example, what will happen is that balloon will be negatively charged. So I'm going to make this a balloon instead. It would have this negative charge. When you bring it next to the wall, even though the surface itself is going to stay neutral, you can actually get a buildup of positive charge right on the surface and get this little bit of attraction. And this little bit of attraction could cause it to stick. So it's what we call temporarily inducing a charge in something. Now you can also permanently induce or permanently charge things if you physically touch something. So if this was negatively charged and I touched it against something, touch it against this, then you are now negatively charged. That's just charging by contact. But we can also do it in kind of a trick way, what we call induction. So if I were to bring this nearby, but I'm not actually going to touch you with it. Instead, I bring my finger nearby and I actually ground you while this charge, this is negatively charged, and I ground you while that negative charge is nearby. What you will see is that you bring the positives near that negative, that the grounding will actually pull other positives up, or we know it's now actually causing the electrons to leave, but it will actually make this positively charged. So if I bring this nearby, but I don't touch, and then I ground you, and then I actually remove everything. Now I actually give you the opposite charge than what I use. So it's kind of a neat way of charging things. We don't do a whole lot with that, but just a couple of things that fit in there. We have a couple of devices that we talk about that can charge things up. One of them is called the Wimshurst generator. This was just using a couple of discs that rotated next to each other using the idea of friction. So after we understand that friction can cause things to be charged, we did a variety of machines get developed. So we talk about the Wimshurst generator. This is a picture of it right there. Another one we're going to talk about a little bit later is called the Van de Graaff generator. But I want to take a kind of a step over here for a second. So J.J. Thompson was talked about in the video with the idea of cathode rays. And so early on, scientists had taken like a glass tube. Okay. And get rid of all the air. So you basically have a vacuum inside. And it's not perfect. It's going to have a whole lot of air. And then inside of this, you also have a couple of pieces that you can connect to electricity. Now, at this time, we still had batteries. Okay, so we'll talk about batteries later, but the idea of a battery. So you had some voltage source, and you need a high voltage. What they noticed is when that happened in this vacuum tube, you would actually get a beam of material. So here, I'm going to change the color of it. I'm going to make it green. So you would actually get a beam that would shine across. And it would always go from the negative post, which is referred to as the cathode, and go to the positive post, which is known as the anode. The beam would go across here. Now, they would actually use a piece of phosphorus so you could see the beam. Otherwise, it was an invisible beam. But early on, they were like, what in the world? This looks like light. But what is actually creating it? And we called them cathode rays just because of where they came from. They were rays coming from the cathode. They thought it might be light, it might be X-rays, it might be some kind of version or another version of that. But the thing that was really weird is if you brought a magnet nearby, so let's say you bring the north pole of a magnet, it would actually cause the light to bend in some fashion, which was weird. It's like, why would that do that? That doesn't make any sense. Also, he noticed if he brought some kind of negatively charged object nearby, it would also cause it to bend. And since we noticed negatives would repel this, they realized that cathode rays were negatively charged. What J.J. Thompson theorized that they weren't actually light at all, but instead these rays were actually electrified particles. And eventually they referred to these electrical particles as electrons, going all the way back to the idea of amber because they have the same charge as the amber. So here's the weird part. Franklin thought it was a positive fluid that was moving between things to make them positive or negative. After J.J. Thompson in the early 1900s, we realized it's not a positive fluid. It's actually negative electrons that are moving. So if you want to make something positive, you don't add positive fluid to it, you remove electrons. If you want to make something negative, you add electrons. You don't remove the positive fluid. So even though Franklin had it wrong, since he had been around for over 100 years with this idea, we just kind of stuck with it. So here's a couple extra things. If you think of the atom, we know electrons are on the outside. That's one of the reasons why they're so easy to move. Plus, their mass here is like 10 to the fourth times smaller. Or actually, this is almost a 10. So it's 10 to the third times smaller. So it's 1,000 times smaller. So it's lighter than the proton and the electron, and it's on the outside. So because of that, it's the thing we can easily move. We also are going to be using this number right here. This is the quantity of charge on an electron and a proton. So it's the standard quantity of charge. It's actually the smallest you can get in nature. Now, you can do things to create ones that are smaller, but in nature, this is the smallest. So this 1.6 times 10 to the negative 19 coulombs. We're going to talk later where it comes from. And the unit, the coulomb, is coming from the fact that it's referred to as, it's named after a person, which is kind of a concept we're going to get to later. But this is a quantity of charge that we're talking about. Not the sign, but the quantity of charge. So you're just adding or removing them. Okay. Why do we call them coulombs? Because we named it after this good old guy, Charles Augustin de Coulomb. Whoops, didn't mean to go back. So in the 1700s, so let's go back to the time frame of Franklin. Not only are we realizing that we have charges, what's causing them, but we want to figure out the force between them since they're attracted or repelled from each other. So what Coulomb did is he was very good at coming up with a variety of experiments to test this. And what he noticed is that the closer they were, the greater the force. The farther away it was, it dropped off. It was actually an inverse squared relationship, very similar to gravity. Interesting. And the amount of charge. So he didn't have a way of knowing that charge. He just came up with multiples. So he would charge something up and say, okay, this is a value of 1. And then he could touch a couple objects together and move them apart. So each one is now a half. And then he would take another object with that half and touch them and pull them apart. And each one is a quarter because things always want to evenly distribute. So that would be kind of the idea. And then he would see, and he noticed that the more charge you had, the more force you had. So it was directly related to that force. And eventually came up with what we refer to as Coulomb's law. So Coulomb's law is this lovely equation right here, that the electrostatic force is directly dependent on the quantity of charge. So Q1 and Q2, the reason why we're in Q building, not only is it heat, now it's the quantity of charge. So it's the amount of charge you actually have. So that affects it, and then it's inversely dependent on the square of the distance here. So very similar to Newton's law of gravity. If you remember, Newton's law of gravity was Fg was big G, mass 1, mass 2 over distance squared. So it's the same, except that instead of talking about masses that attract each other, it's actually charges that are attracting or repelling, which is kind of neat. Plus, this was the universal gravitation constant. This is the electrostatic constant. It has a value of 8.99 times 10 to the ninth. Later on, we're going to talk about this part, that it also can be related to a thing called the permittivity of free space. But for right now, we'll just worry about the 8.99 times 10 to the ninth. Then I think I just finished out with a couple of little sample problems, which are also in the note or in the Google form. So I think we'll just kind of let you finish this out. If I had a proton, which has a charge of positive 1.6 times 10 to the negative 19, and an electron, which is negative 1.6 times 10 to the negative 19, would they be attracted or repelled? Well, one's positive, one's negative, so we know it's got to be an attractive force. That's the only thing I use for that part. Then part B, what is the magnitude of the electrostatic force between the electron and proton? Well, that would be right there. So I would be putting in, so Q1 would be the charge of the proton. So that'd be the 1.6 times 10 to the negative 19 coulombs. It's a positive. And then this would be the charge of the electron, which is also 1.6 times 10 to the negative 19 coulombs. It's technically negative, but if you notice, I would put absolute values in here. Really, it just means I would just want the quantity. I don't want the sign of it. So we put that in, and then we know this is how far apart they are. So this would be your radius. That would be the R, right in there. You could chunk it out, put in this for K, and you're all set. I threw in C just if you wanted to have a little fun with this. It says, what's the speed of the electron? If it was truly in orbit, how fast would it be going? If it had to do an orbital motion as opposed to just be an electron cloud. What I'm basically borrowing for this, and this is totally if you want to do this, then your force, this electrostatic force, would equal the centripetal force. So you would have K Q1 Q2 over R squared would equal mv squared over R. I'm not going to bother with this and try to solve for V, but it's just something fun if you wanted to try it out. You could do charges on a line, so we could figure out the net force on Q1 here. And so in the Google form, I go into how do we figure out the direction of the force, or how much force there is. We know that Q1 is positive, so it's attracted to this. So there'd be an attractive force this way. And then this is positive, it would be attracted to this. Here, let's change out my color. Let's make this red. So it would also feel an attraction this. Which one of those is bigger? Well, think about it in terms of two things. Magnitude of the charge is going to affect it. Larger magnitude, so a 3 and a 7 is larger than a 4 and a 3. So that's going to make this one a little bit larger. Okay. Also, it's inversely dependent on the radius. This is smaller than this one, so a smaller radius, larger force. So I would say the force to the right is going to be greater than the force to the left. So it would definitely be pulled to the right. And then we could use the equation to actually solve for it. That's a little bit of the beginning on electrostatics, electric forces, Coulomb's law, that type of stuff. Hope you enjoyed.